Don't forget you have an assignment. I believe that assignment is due today because it is Friday because I posted it on Monday. Um, I know only a few people have handed it in so far. But so far, the assignment looks pretty good from the ones that I did grade. And I haven't gotten really any questions on this assignment. Last week I got a lot of questions on the weekly. This week I've gotten nothing. Most of the students do follow me, so I mean they know I'm live. They're just not coming. I also send out that remind every single day, so everyone is aware. I think everyone in the class knows when I start. I know at least 6 of you are consistently watching afterwards, which is good too. But we're gonna jump right into it. We're just gonna learn, which something I think is considered pretty easy for the most part. It comes up a lot, and there's a lot of ways it can be utilized because of the nature of this topic, which are tangents. Different from the tangents that we learned in with SOHCAHTOA tangents, we did mention previously that tangents, as defined over here, is a tangent line is a line that intersects at exactly one point, which is something we defined right at the beginning of the unit, was this idea. So in this diagram right over here, AB is tangent. That's really all we've ever discussed with tangent lines up to this point. Now we're going to have to kind of discuss is why is that even important for our sake, and what do tangent lines really mean on a geometry scale. It says a line is tangent to a circle if and only if it is blank to a blank drawn to the point of tangency. So it's going to be perpendicular if and only if it is perpendicular to a radius or diameter. Drawn to the point of tangency. So again, if you look at the diagram over to the left, AB is a tangent, and line segment PA is a radius. Whenever a radius connects to the point of tangency, they will always form a right angle right here. And the reason why this topic can be so diverse is because we've done so much with right angles up to this point. Anything we've ever done with right angles could come up with this topic. We could throw SOHCAHTOA at you. We could do Pythagorean theorem. We could do hypotenuse leg proofs. There are so many different topics and avenues we could kind of jump into with this topic. Today we're only really going to, we're going to use a lot of Pythagorean theorem with this, but that does not mean it's going to be necessarily always Pythagorean theorem. Anything we've ever seen with right angles, so it could be right triangles, SOHCAHTOA, like I said, they could throw at you if you have a diagram that has a tangent and a radius drawn. I see a lot of triangle similarity with this topic, where they have 2 different triangles, they're both right triangles, you can prove that they're similar. So there's a ton that we can do. The most important thing for you to do is recognize if there's a tangent drawn, like we have here in AB, and a radius is drawn, that right angles are formed. That's the most important thing that you are able to recognize, and then from there you can go into really any avenue that consists with right angles. But like I said, most of what we're going to do today is practicing using this idea with Pythagorean theorem. But don't think that, tangent lines means we're probably using Pythagorean theorem. No, not necessarily. It could be absolutely anything. It just depends on what the question is. We just don't have time to go over every possible example they could throw at you, because then this could take days. Like I said, the most important thing you know is that these form right angles and what that could do to a problem. So let's look at number one. It just says determine if AB is tangent. So they're not saying it is tangent. They're telling me to determine yes or no if this is tangent or not. So how are we going to determine if that line segment is tangent? Well, we are kind of asking ourselves, is this a right angle? And what evidence could we use to determine if this is a right triangle? Well, we know it's a right triangle if Pythagorean theorem works. That's the best way to determine if a triangle is in fact a right triangle. And they gave us all the sides, 8, 15, and 17. So I'm really asking myself, is a squared plus b squared really equal to c squared? That's kind of what we're determining. We're determining, is that equal sign really the right thing to be there? If yes, it's a right triangle, and if it's a right triangle, AB is certainly tangent. If Pythagorean theorem does not work, that means this is not a right triangle, which means AB cannot be tangent. Because one thing is clear, PA drawn here is the radius to this circle. So let's just do Pythagorean theorem. We're just seeing if Pythagorean theorem works, yes or no. So we have 8 squared plus 15 squared, the two small sides. Is this equal? Still, I'm going to put a question mark there because I don't know. Is this equal to 17 squared? So I got my calculator out. I know 8 squared and 15 squared are 64 and 225. 17 squared I don't know off the top of my head, so I'll use my calculator to figure that one out. I get 289. 289. And then I'm asking, is 64 plus 225 the same as 289? And I can see just from looking at it that yes, they are in fact equal to each other. So we get 289 is equal to 289. So now I don't need that question mark anymore. I know for sure that Pythagorean theorem works, and yes, that this is tangent. So we just got to answer the question. Yes, AB is tangent since triangle ABP is a right triangle. And we know it's a right triangle now because the Pythagorean theorem showed us that it was in fact. All right, we're going to do the same thing with number 2. Same idea, we just have different numbers now. We have 11, 5, and 14. There is one slight problem with this one, though, and it's that 5. You'll notice that this, if this is in fact a right triangle, that should be the hypotenuse to that triangle, which is, this is what we're trying to figure out. Is that a right angle? If that's a right angle, you know, that's how we can determine if AB, again, is tangent or not. But in this diagram, clearly 5 can't be the longest side. So we have to expand our idea of the circle and kind of be aware of that this point on the circle, I'll highlight it, to here, there's 2 radii drawn in the diagram. 11, which is the number that you want because it's part of the triangle, but that green part is also 11 because it's a tangent. Remember, any line that extends from the center of the circle to on the circle is going to be exactly the same. Is there any way we could prove it's a right triangle using SOHCAHTOA? That's a really good question. I want to say yes, there is. I think it might be a little, oh, no, I guess it wouldn't be too advanced for us. You could. They'd have to give you an angle measure, though. Basically, if I'm going to answer Paige's question, if I don't know what these angles are supposed to be, but if they said this was 20 degrees, you probably could use SOHCAHTOA to prove this. You could do, the sine of, I don't know, the sine of 20 would equal 8 over 17. And you're seeing, in this case, does the sine of 20 equal 8 over 17? If this is true, if 8 over 17 is the same thing as the sine of 20, then yes, it would be a right triangle. I don't know if it would... the reason I don't know if they would do this is because these numbers, like the sine of 20 is going to be an irrational number. And that's what we need to kind of look out for. So are they going to match exactly in the calculator? Probably not, which is why I don't think they would ever ask you SOHCAHTOA. However, there are some SOHCAHTOA values that do work out to be good values, like the sine of 30 is 1/2. So they could do that. So you could use SOHCAHTOA. It's definitely a little bit more tricky, but it's definitely something we could do. Could you take the tangent of 90? Whenever we're doing SOHCAHTOA, we should never start with the 90-degree angle. Especially tangent, because I'm pretty sure the tangent of 90 is undefined. I'm pretty sure if you plug in tangent 90 in the calculator, you're going to get undefined. 90, tan, yeah, you get my calculator says overflow. That just means it's undefined. Don't take the sine of 90, cosine of 90, or tangent of 90. We might do something at the end of this unit that's going to prepare you for trig, where we will actually take the sine of 90, cosine of 90, and tangent of 90 and kind of look at them a little bit more deeper. I know that's a long explanation for your question. So I want to say yes, it's possible they could ask you. I want to say it's unlikely. Going back to this one. So that highlighted segment is the radius of the circle. We know the radius of the circle is 11. And if the radius of the circle is 11, that makes that whole side that hypotenuse. I'm going to, quotation hypotenuse, because I do not know if it is hypotenuse or not. But I know it's 16. So now I can do my Pythagorean theorem using 14 squared, 11 squared, and now that is truly the longest side, 16 squared. So we're going to do the same thing. Is a squared plus b squared actually equal to c squared? We have 14 squared plus 11 squared. Is that equal to 16 squared? So 14 squared, I think that's 196 plus 121 for 11 squared. 16 squared is 256. And I'm starting to see that this is not going to be equal. I actually don't know what... I just know that 1 plus 6 here is going to be... This number is going to end in a 7. And it should end in a 6. So I'm kind of concluding that this one is not going to be a right triangle, because 196 plus 121 is 317. And 317 is not equal to 256. So the conclusion here is, because Pythagorean theorem does not work, that means this triangle is not a right triangle. It is just some scalene triangle that has 3 different angles. Is not a right triangle. Therefore, AB is not tangent to circle P. Since triangle ABP is not a right triangle. So that's just one way we can utilize the tangent to the circle. Like I said, today we're really just going to do a lot of Pythagorean theorem, but it could be anything with right triangles. Now, for 3 through, I think really for the rest of this page, it says if JK is tangent. So now we don't need to see if Pythagorean theorem works. Now we know Pythagorean theorem has to work because they are giving me something completely different. And this actually makes it easier in my opinion. If they just tell you it's tangent, that means if there's a radius or diameter drawn, it's a right triangle, always. So you don't need to see if Pythagorean theorem works. Now we can assume that Pythagorean theorem absolutely will work. And our goal is, in all the diagrams, just figure out the value of x. And sometimes these can be tricky. I'm pretty sure there's a tricky one somewhere on this page. And we'll take a look at that. I think like some of the last ones, they can get a little tricky. But let's take a look. So in this case, just identify where the right angle should be. So here's my tangent, JK. Here's the radius, JL. Those are the two that are perpendicular to each other. So therefore, the right angle's right there. That way you can identify clearly what the hypotenuse should be. Because obviously we know the hypotenuse is always directly across from the right angle. So x is the longest side. So x is your c term, your c squared term. So when I'm doing Pythagorean theorem, because I know some people still have a habit of just doing whatever two numbers they give you as a and b. Don't make that habit. In this case, it will be just that. So we have 7 squared plus 19 squared equals x squared. So we get 49 plus 19 squared. I actually don't know what 19 squared is. I'm going to say it's like 361. That's what I'm going to guess. Oh, that was good. That was a good guess. Equals 49. And just by looking at this, I don't think we're going to get a whole number here. I think, because the left-hand side, I think, is now 410. 410 is not a perfect square. So we do need to take the square root of both sides. And 410 square rooted, definitely not going to be a perfect square. So square root it. We'll round everything to the nearest tenth for our sake. So I get 20.24. So 20.2 I will put for my value of x. Pretty straightforward. Then we get to number 4. Number 4 is similar to number 2. They don't give you all the proper information. And actually, they use the same value of the radius here. Again, we're making the assumption, or they've told us, it's not an assumption, they told us that JK is tangent to the circle. So that's why I can put that right angle right in there, because the radius is JL. So in this case, we have our right triangle right here. But this 7 is only this outside piece. But because that radius is drawn in, I know that this is in fact 11 because all the radii are going to do the same value. They're all going to be 11. That makes this hypotenuse of the triangle 18. Which now that part is the c squared. So when we plug into Pythagorean theorem, we got to make sure we plug in correctly into a squared plus b squared equals c squared. Doesn't matter which one you call, a or b. I'll call a 11. And in this case, b squared, that's what I'm looking for. So it's really, you can keep it b squared. I'm going to substitute it with the x because that's the variable we're looking for. And then c is the hypotenuse, 18 squared. 11 squared is 121 plus x squared equals 18 squared, 324. So I can subtract 121 from both sides. And I get 203. And I know that 203 is definitely not a perfect square, so I'm going to get another decimal. We'll just take the square root of both sides. Let's see what our calculator gives us. 14.24. So 14.2. Let's keep going. All right, number 5 I think starts getting a little trickier. There might be more than one way to do this, but there's a few ways we can do this. We can make this really hard on ourselves. We could also make it really easy. One thing's for sure, that the value of this is 10. And if we're doing Pythagorean theorem, well, here's our right angle. There's the tangent meeting the radius. So we know that's a right angle right there. And I kind of want to do both ways. I want to do the hard way. I also kind of want to do the easy way. We'll do the hard way first, which is we can use Pythagorean theorem. The problem is that this side right here is 10 plus x. The reason that's a problem is we have to then square an expression. And once you realize you're going to be squaring an expression, this is going to turn into a quadratic. Actually, I changed my mind. We're not going to do it the hard way. Reason is because there's not enough room. It would take up a lot of room. But you would get a quadratic. It is, and it's completely fine to solve it this way. Meaning you could just type, you could plug in 10 plus x squared. You would have to do your box method to expand that out, because it would be like x squared plus 20x plus 100. And then you could, continue doing Pythagorean theorem equals 24 squared plus 10 squared. The easier way to do that is, let's just call the hypotenuse C. Because you have the other two legs. You have 10 squared and 24 squared. So you could easily just figure out the entire hypotenuse. And then when you have the entire hypotenuse, you could just subtract that 10 from it to figure out the value of x. Which is going to be far easier than running into a quadratic. But we should all be familiar with solving quadratics. We've done it a few times this year. You did it a lot last year, and I don't want us to forget that skill. That it's a possibility that could come up. And also to prepare you for next year, you're going to be running into quadratics all the time in Algebra 2. But we'll do the easy way just because we don't have a lot of room. If anyone wants to do the hard way, you'll get the same answer. But we'll jump into a squared plus b squared equals c squared. That's 24 squared plus 10 squared equals c squared. And I am purposely calling it c now because I'm finding the entire hypotenuse as a whole instead of the answer x. So 24 squared is going to be, I'm going to go with 496. Oh, I was way off. 576. Oh, that makes sense. Plus 100 equals c squared. So add 100 to that. That is going to be 676 equals c squared. We'll square root both sides. This might be 26. It is 26. So the hypotenuse is 26. So if the entire hypotenuse is now 26, this whole thing, the value of x is just this piece right here. And we know the radius is 10. We can just subtract 10 from it. So the answer is 16. But by all means, if anyone wants to do a quadratic, Go for it. We'll do one more. I think I'm going to jump to number 8. I like number 8. And then we're going to look at the other side and look at some other properties. Because when we finish this, we're only going to have about 10 minutes left. And I want to make sure we go over the other parts of, the other things that we could see with tangent lines. They're pretty easy. But that way on Monday, we can start fresh, start with something completely new, different property of circles. But let's take a look at number 8. So number 8 looks pretty straightforward. They give us the in this diagram they give us a diameter instead of just the radius, but that's fine because it's still technically a radius, and the tangent is still kj, so the right angle is right there. The problem is the diameter is one of the sides to the triangle, and they only give you the radius, which is x. And there's no other information to figure out what the actual value is going to be. So we have to just call the other radius x, which makes the diameter x plus x, or 2x. And again, you could run into a quadratic here because you do have a 2x there. When you square it, you're going to have it's not going to be x squared anymore. Luckily, we're not going to run into a quadratic, but we'll see what happens because there is a little bit of a different process. Still going to use Pythagorean theorem. The hypotenuse in this case is 25. So that makes a and b 7 and 2x respectively. So 7 squared plus, in parentheses, 2x squared equals 25 squared. So 7 squared is 49 plus, you have 2x squared, so you have to square each thing in the parentheses individually. It's because it's 2x times 2x, and if you see it written like that, 2x times 2x, that probably makes a lot more sense. 2 times 2 is 4. X times x is x squared. So it's 4x squared. Equals 25 squared is 625, or 25 times 25. And now we haven't really seen a number in front of the x squared in a long time, but we're going to basically solve it exactly the same. Get x squared by itself. So my first step here is, I can't do anything with that 4, but I can subtract both sides by 49. So 625, so 625 minus 49, and I get 576. So 4x squared equals 576. Now I can deal with that 4. Don't take the square root of both sides. I suppose in this specific example you could, because 4 is a perfect square. But what I prefer you to do, because if it were like 5x squared, I would not want to take the square root of both sides. It just happens to work for this one. You should just divide both sides by 4 first, and then we'll take the square root after. So when you divide both sides by 4, 576 divided by 4 is 144. So I'll move my work up here. X squared equals 144. Now we can square root it with no problems. And 144 is great because that's a perfect square. X equals 12. So as long as your algebra is, still pretty good, this all should be fine. But again, most important thing out of all this stuff on this page is the new concept of when a radius or a tangent comes in contact with when a radius or diameter comes in contact with a tangent, they form right angles. That's really the most important thing. Like I said, every day is just a new thing about circles. That's the new thing about this one. And they could ask it in so many different ways. I think that's why I make circles challenging for some students. There's so many different ways they could tie in circles. You have to just be really good and know the different theorems. Because now we've done central angles, inscribed angles, and now tangents. Where there's more properties as well with tangents. That was just one. Couldn't we also do the same thing we did for 5, find the entire hypotenuse and then divide by 2? Yeah, we absolutely could have. Yep. And just called it like A or B. Yep, Paige is absolutely right. That is a different way we could have done it. So there's going to be two more, one more property with tangent lines. That doesn't necessarily have anything to do with perpendicular lines, which is this rule right here. It says if two segments from the same external point are tangent to a circle, then they are congruent. So what that means, so if two segments, in this case the two segments in question here are AB and BC, those are our two segments. The same external point is B. So external point means outside the circle. So if you draw any point outside the circle, that means there is a possibility you could draw two tangents depending on what direction they go in. No matter what point you draw, if I draw a point all the way out here, you could draw a tangent going in this direction, and you could draw a tangent in this direction. As long as it hits the circle once. You always have two options. But no matter what, both of those tangents will always be congruent to each other. So that is what this idea is saying. If you have an external point outside the circle, you draw both tangents to the circle, those line segments are going to be congruent to each other. So it says right here that AB is congruent to CB. And then if a polygon is circumscribed around a circle, then all sides are tangent, meaning there's a circle drawn inside, and circumscribed means that all of the points on the circle are essentially tangents, that F only hits the shape of the polygon once. D hits once and D hits once. That means you have 1, 2, 3, 4, 5. There are 6 different tangents, 3 external points. But based on the other rule we just described, well, that means that these two line segments are congruent to each other. And below it, that means EC is going to be congruent to the line segment that's also connected with point C. So these two tangents are congruent. And then from point A, 1, 2, 3, 1, 2, 3. All 3 points here are congruent. So these questions are common. They could ask you about perimeter, certain values of line segments, and so forth. As long as we know if something is circumscribed in something, it's hitting the polygon or circle in one spot only. And that goes right back to the definition of a tangent. If it's hitting in only one spot, that's exactly what tangents do. They hit in one and only one spot. Which, no surprise, these aren't going to be too bad as long as you, of course, recognize the new rule, the new geometric theorem that is kind of being presented to you. Because if we're just told that AB and CB are tangent, the directions say assume segments that appear tangent are tangent. Usually directions aren't like that vague, but in this case it's fine. So in this one, we're assuming these are tangent. They're drawn from the same external point, B. They're simply congruent to each other. Set them equal. 5x plus 23 equals 8x minus 19. Solve for x. Subtract 5x. Add 19. Uh-oh. I still don't know why that happens. That should be better. Maybe not. Oh no, it's all messed up. I'm not sure why it's doing this. It might just look a little distorted, but we only have a few minutes left, so I want to make sure we do it. Finishing this one up, we get 3x is equal to, what was that, 42? And then we can divide both sides by 3. So that's 14. And we'll do one more to practice the other theorem right there, the circumscribed polygon one. So I'm going to jump down to 13, where it just says find the perimeter of triangle DEF. So triangle DEF is the entire triangle, and we're assuming that all the points are tangent from their respective external points. So that means these are congruent. But if we know one is 11, the other one is 11. Then on the other side, HE is tangent to EI. One is labeled as 16. The other one must also be 16. And then same thing with this one. 9.5, that means FG is also 9.5. Add them all together. So you add all 6 numbers together. So we have 11 plus 11 plus 16 plus 16 plus 9.5 plus 9.5. Oh, I think I hit 9.8 twice. 19 plus 22 plus 32. 73. All right. I think that's a good spot to end. We might do a little bit of practice with some of these on Monday because we only did one example of each. And like I said, it's good to recap all these theorems. But it's Friday. Enjoy your weekend. And I'll see you guys on Monday. And I'll stick around if you guys have any specific questions about anything. Don't forget about that assignment in Google Classroom. But yeah, have a nice weekend, guys. I'll see you later.